Close your eyes and imagine standing on solid ground. You feel the earth beneath your feet, steady, unchanging, permanent. But this solid surface is just the thinnest skin on an immense sphere of rock, metal, and heat. Beneath you lies a world more alien than the surface of Mars, more extreme than the depths of space. Tonight, we embark on an impossible journey descending through thousands of miles of rock and metal to reach Earth's center. We'll travel through the crust where we live, into the mantle where rock flows like honey over millennia, past the liquid iron outer core, and finally to the solid inner core, a ball of crystalline iron as hot as the sun's surface, suspended in the heart of our planet. This is a journey no human has made or ever could make. The deepest hole ever drilled barely scratched the surface, just 7.5 miles down in a planet 8,000 miles across. Yet through earthquakes, experiments, and careful deduction, we've mapped Earth's interior in extraordinary detail. We know what lies beneath, even though we've never seen it directly. Prepare to discover a hidden world of unimaginable heat and pressure, where diamonds form and continents drift, where the magnetic field is born and mountains have roots extending miles into the earth. Our journey begins at the surface, where we live our entire lives without ever penetrating more than a few hundred feet down. The ground beneath our feet feels solid and permanent, but it's merely the uppermost layer of a dynamic, ever-changing planet. Earth's crust is the thin, solid, outermost shell, the skin on the planet's surface. Like the skin on an apple, the crust is remarkably thin compared to Earth's total radius. On continents, the crust averages about 20 to 25 miles thick, though it can reach 45 miles beneath major mountain ranges. Under the oceans, the crust is even thinner, typically just 3 to 6 miles thick. This oceanic crust is the youngest and thinnest part of Earth's solid surface, constantly being created at mid-ocean ridges and destroyed in subduction zones. The continental crust is fundamentally different from oceanic crust. Continental crust is older, some rocks are over 4 billion years old, and composed primarily of granite and other light, silica-rich rocks. These rocks are less dense than oceanic crust, which is why continents float higher on the mantle below, creating dry land above sea level. Oceanic crust, by contrast, is primarily basalt, a denser, darker rock formed from cooled lava at mid-ocean ridges. Standing on the surface, you're at the interface between Earth's solid interior and its fluid exterior, the atmosphere and oceans. This interface is surprisingly active. Water from rain and rivers percolates down through cracks and pores in the rock. In some places, this water reaches depths of several miles before returning to the surface as hot springs or geysers. The deepest groundwater circulates through the upper crust, heated by Earth's internal warmth. The deepest humans have physically gone into Earth is about 2.5 miles the depth of the deepest mines, primarily gold and diamond mines in South Africa. These mines are hot, often over 130 degrees Fahrenheit, 55 degrees Celsius, requiring massive air conditioning systems to keep them workable. The rock walls are under enormous pressure from the weight of overlying rock, and mine shafts must be carefully reinforced to prevent collapse. The deepest hole ever drilled is the Kola super-deep borehole in Russia, completed in 1989. It reached 7.5 miles, 12.2 kilometers, deep barely 1/6 of the way through the crust beneath it. The project took 20 years and encountered temperatures far higher than expected, about 356 degrees Fahrenheit, 180 degrees Celsius at the bottom. The heat and pressure made drilling deeper impossible with available technology. At those conditions, rock becomes plastic and flows into the borehole, making further progress futile. What scientists learned from Kola was fascinating. They found water at depths where it shouldn't exist, apparently squeezed from crystal structures in the rock by extreme pressure. They discovered microscopic fossils of single-celled organisms at depths of 4 miles. They found that seismic discontinuities in the crust, previously thought to mark transitions between rock types, actually represented zones of fractured, water-saturated rock. These discoveries reminded scientists that even the crust, the most accessible part of Earth's interior, holds surprises. The temperature increases as you descend. Near the surface, temperature rises about 25–30 degrees Celsius per kilometer of depth, the geothermal gradient. This heat comes from two sources: primordial heat from Earth's formation 4.5 billion years ago, still slowly escaping, and radioactive decay of elements like uranium, thorium, and potassium in the crust and mantle. These radioactive elements decay over billions of years, releasing energy that keeps Earth's interior hot. As we descend through the crust, the rock changes. Near the surface, rocks are sedimentary sandstone, limestone, shale, formed from accumulated sediments. Deeper, we encounter metamorphic rocks, rocks that were buried, heated, and compressed, transforming into new forms. Limestone becomes marble, shale becomes slate, then schist. Deeper still, we find igneous rocks, granite that cooled slowly deep underground, or basalt from ancient volcanic intrusions. The crust is not uniform. Beneath continents, it's thick and complex, with multiple layers representing billions of years of geological history. Beneath oceans, it's thin and young, nowhere older than about 200 million years. This asymmetry reflects plate tectonics, the process that constantly reshapes Earth's surface. At the base of the crust, we encounter the Mohorovičić discontinuity, the Moho discovered in 1909 by Croatian seismologist Andrija Mohorovičić. He noticed that seismic waves from earthquakes suddenly accelerated at a certain depth, indicating a transition to denser rock. The Moho marks the boundary between crust and mantle, where rock composition changes from crustal rocks to mantle peridotite. No one has ever sampled the mantle directly beneath the Moho, except in a few rare places where tectonic activity has thrust mantle rocks to the surface. Projects to drill through the oceanic crust to the mantle have been proposed. The oceanic crust is thinner, making this more feasible, but none have succeeded yet. The transition from crust to mantle represents our first major boundary in our journey downward. Before we cross the Moho, let's appreciate the crust's role. This thin layer is where all known life exists. It contains all the minerals we mine, all the fossils revealing Earth's history, all the soil that supports agriculture. It's the interface where Earth's interior heat meets the cold of space, creating the temperature gradients that drive weather and ocean currents. The crust is our home, the only part of Earth we directly interact with. But it's time to leave the familiar and descend deeper, crossing the moho into the mantle, a realm of extreme pressure and temperature, where rock behaves in ways contrary to everyday experience. Crossing the moho, we enter the mantle, the thick layer of rock between crust and core, making up about 84% of Earth's volume. The mantle extends from the base of the crust down to 1,800 miles, 2,900 kilometers depth. Though solid rock, the mantle flows slowly over geological time, driving plate tectonics and volcanic activity. The uppermost mantle is relatively cool and rigid, forming the lower part of the lithosphere, the solid outer shell that includes the crust. The lithosphere is broken into tectonic plates that move across Earth's surface. Beneath the lithosphere lies the asthenosphere, where mantle rock is hot enough to be partially molten and ductile, allowing the lithospheric plates to slide over it. The boundary between lithosphere and asthenosphere isn't sharp, it's a gradual transition occurring at different depths depending on temperature and composition. Beneath old, cold continents, the lithosphere can extend 120 to 150 miles deep. Beneath young ocean floor near mid-ocean ridges, it may be only 5 to 10 miles thick. The asthenosphere begins around 50 to 120 miles depth and extends to about 400 miles. In this zone, rock is close to its melting point. A few percent of the rock is molten, existing as tiny droplets between solid crystals. This partial melting makes the rock weak and ductile, allowing it to flow slowly, perhaps a few centimeters per year. Over millions of years, this flow drives tectonic plates apart at divergent boundaries and drags them down at subduction zones. The mantle's composition is primarily peridotite, a dense rock rich in olivine and pyroxene minerals containing iron, magnesium, silicon, and oxygen. Unlike the diverse rocks of the crust, the mantle is relatively uniform in composition, though its mineralogy changes with depth as pressure forces atoms into denser crystal structures. Temperature in the upper mantle ranges from about 1,000 degrees Celsius, just below the moho, to around 1,500 degrees Celsius at 400 miles depth. These temperatures would melt rock at surface pressure, but the immense pressure keeps the mantle solid except for the small partial melt fraction in the asthenosphere. Pressure at 100 miles depth is about 40,000 times atmospheric pressure. At 400 miles, it's over 140,000 atmospheres. At these pressures, matter behaves strangely. Rocks that are brittle at the surface become ductile, flowing like very stiff honey over long time scales. The mantle-convex hot rock slowly rises, cools, and sinks in vast circulation patterns that take millions of years to complete. This convection is the engine driving plate tectonics. Mantle convection works like this. Radioactive decay and primordial heat warm the deep mantle. Warm rock is slightly less dense than cold rock, so it rises slowly, perhaps a few centimeters per year. As it rises and pressure decreases, it may partially melt, producing magma that can erupt as volcanism. The rising rock spreads horizontally beneath the lithosphere, cools, becomes denser, and eventually sinks back down in subduction zones where tectonic plates converge. This process is visible at Earth's surface, mid-ocean ridges, underwater mountain ranges where tectonic plates diverge mark locations where hot mantle rises. Magma erupts along the ridge, creating new oceanic crust. The new crust spreads away from the ridge as more magma erupts. Eventually, old oceanic crust reaches a subduction zone where it descends back into the mantle, completing the cycle. Subduction zones are remarkable features. Here, oceanic lithosphere, typically 100 plus million years old, and cold plunges into the hot mantle. The descending slab remains colder than surrounding mantle for millions of years as it sinks. Seismic tomography using earthquake waves to create 3D images of Earth's interior reveals these cold slabs extending hundreds of miles into the mantle. Some slabs reach all the way to the core mantle boundary over 1,800 miles down, showing that mantle circulation involves the entire mantle depth. As rock descends in subduction zones, increasing pressure forces minerals into denser forms. At about 250 miles depth, olivine transforms into a denser structure called wadsleyite. At 410 miles depth, wadsleyite transforms into ringwoodite. These phase transitions are detectable by seismic waves and mark the boundary between upper and lower mantle. The transition zone between 410 and 660 miles depth is particularly interesting. Here, ringwoodite transforms into even denser minerals, bridgmanite and ferropericlase that make up the lower mantle. This transition is associated with a seismic discontinuity at 660 kilometers depth, visible in earthquake data worldwide. The 660 km discontinuity may act as a partial barrier to mantle convection, with some slabs stalling there temporarily before sinking further. Water plays a surprising role in the mantle. Though the mantle is solid rock, tiny amounts of water are bound in crystal structures. Minerals like ringwoodite can contain up to 2 to 3% water by weight. The transition zone may hold vast amounts of water, potentially more than all Earth's oceans combined. This water is released when subducting slabs cross phase boundaries, contributing to volcanism above subduction zones. Mantle plumes are another fascinating feature. These are narrow columns of hot rock rising from deep in the mantle, independent of plate tectonics. When a plume reaches the lithosphere, it creates a hot spot, a volcanic region like Hawaii or Yellowstone. Unlike volcanic arcs at subduction zones, hotspots can occur far from plate boundaries. As a tectonic plate moves over a stationary plume, it creates a chain of volcanoes, with the oldest volcanoes farthest from the current hotspot position. The Hawaiian Islands formed this way. The Big Island of Hawaii sits over the hotspot now, with active volcanism at Kilauea and Mauna Loa. Older islands stretch northwest, Maui, Oahu, Kauai, with ages increasing with distance from Hawaii. The chain continues as the Emperor seamounts, underwater volcanoes extending thousands of miles northwest, tracing the Pacific Plate's motion over the past 80 million years. Diamonds form in the upper mantle, typically at depths of 90 to 120 miles, where pressure and temperature are right for carbon to crystallize into diamond rather than graphite. Volcanic eruptions from deep mantle sources occasionally carry diamonds to the surface in kimberlite pipes, rare volcanic conduits that ascend rapidly from great depth. The diamonds are xenocrysts, foreign crystals that didn't form in the kimberlite but were picked up from surrounding mantle during ascent. Some diamonds contain inclusions, tiny crystals of other minerals trapped when the diamond formed. These inclusions provide direct samples of the mantle, revealing its composition and conditions. A few rare super deep diamonds contain inclusions of ringwoodite or other transition zone minerals, proving they formed at 250 to 400 miles depth, far deeper than typical diamonds. As we descend past 400 miles depth, we leave the upper mantle and enter the transition zone. Here, pressure exceeds 500,000 atmospheres. Temperature is around 1,700 degrees Celsius. Rock has undergone multiple phase transitions, packing atoms into ever denser configurations. The transition zone is relatively thin, only 250 miles thick, but crucial for mantle dynamics. It may determine whether mantle convection involves the whole mantle or separates into upper and lower layers. At 660 miles depth, we cross into the lower mantle, where pressure exceeds 240,000 atmospheres and temperature reaches 2,000 degrees Celsius. We're now over 1/4 of the way to Earth's center, having passed through the crust and upper mantle. But the journey's most extreme conditions still lie ahead, in the lower mantle and core below. Crossing the 660-kilometer discontinuity, we enter the lower mantle, the largest single layer of Earth by volume, extending from 660 miles to 1,800 miles depth. The lower mantle contains about 56% of Earth's total mass and stretches across a distance greater than Earth's radius. The lower mantle is dominated by two minerals, bridgmanite and ferropericlase. Bridgmanite is a magnesium-iron silicate with a perovskite crystal structure, the densest way to pack these elements at lower mantle pressures. Ferropericlase is a magnesium iron oxide. Together, these minerals make up about 90% of the lower mantle's volume. Bridgmanite is Earth's most abundant mineral, making up about 38% of the planet's volume. Yet it was only confirmed to exist in nature in 2014. This is because bridgmanite is only stable at extreme pressures. Bring it to the surface and it transforms into other minerals. The only natural bridgmanite samples we have come from shocked meteorites, where impact created momentary extreme pressures that formed tiny bridgmanite crystals, later preserved as the pressure dropped rapidly. The lower mantle is hotter than the upper mantle, with temperature increasing from about 2,000 degrees Celsius at the top to perhaps 3,500 degrees Celsius at the bottom, near the core mantle boundary. Pressure increases from 240,000 atmospheres to 1.3 million atmospheres. At these conditions, rock behaves very differently from surface rocks. Viscosity resistance to flow is key. Despite being solid, the lower mantle flows slowly over geological time, but it's much stiffer than the upper mantle. Where the upper mantle has a viscosity perhaps 100,000 times that of honey, the lower mantle's viscosity is 10 to 100 times higher still. This means convection in the lower mantle is slower. Rock may take hundreds of millions of years to circulate, compared to tens of millions in the upper mantle. Seismic tomography reveals the lower mantle's structure in 3D. Fast seismic regions, where waves travel quickly, correspond to cold, dense rock, typically ancient subducted slabs that have reached the lower mantle. Slow regions correspond to hot, buoyant rock, likely plumes rising from near the core. These images show that mantle convection is complex, with slabs, plumes, and large-scale circulation all occurring simultaneously. Two massive structures dominate the lowermost mantle. These large low shear velocity provinces, LLSVPs, nicknamed superplumes or blobs, sit above the core mantle boundary beneath Africa and the Pacific. Each is thousands of kilometers across and hundreds of kilometers thick. Seismic waves slow dramatically when passing through them, suggesting they're hotter and possibly chemically distinct from surrounding mantle. The origin of LLSVPs is debated. They might be accumulations of subducted oceanic crust, which is denser than normal mantle and collects at the bottom. They might be primordial material left over from Earth's formation, never mixed into the convecting mantle. They might be partial melt regions where the lowermost mantle is hot enough to be partly molten. Whatever they are, they're long-lived features that influence mantle convection. Many mantle plumes seem to originate at the edges of LLSVPs, where hot material from the core mantle boundary rises. The African and Pacific superplumes may act as plume generation zones, producing the hotspots we see at the surface: Hawaii, Iceland, Reunion, Kerguelen, and others. This connects surface volcanism to deep mantle structure in unexpected ways. Subducted slabs reach the lowermost mantle in some regions. Tomographic images show slabs descending all the way to the core mantle boundary beneath parts of the Western Pacific and South America. These slabs are colder and denser than surrounding mantle, sinking through the entire mantle depth. They accumulate at the bottom, forming slab graveyards that may eventually heat up and contribute to upwelling plumes millions of years later. The lower mantle is relatively homogeneous compared to the crust and upper mantle. It doesn't have the layering and compositional diversity of the crust, nor the phase transitions of the upper mantle. It's mostly bridgemanite and ferropericlase, with composition varying slightly depending on temperature and the history of the rock, whether it's old oceanic crust, subducted sediment, or original mantle material. But the lowermost mantle, the region within about 150 miles of the core, is special. This region, called the D layer, pronounced D double prime, has unusual properties. Seismic waves behave strangely here, suggesting complex structure. Temperature increases dramatically, from perhaps 3,500 degrees Celsius to 4,000 degrees Celsius across the 150-mile thickness, because of heat coming from the core below. The D layer may be partially molten in places. It likely has chemical heterogeneity variations in composition from mixing of subducted crust, primordial material, and reactions with the iron core. Some regions of D have ultra-low seismic velocities, suggesting partial melting or unusual compositions. Other regions have sharp boundaries and layering, indicating complex dynamics. D is where mantle plumes originate. Hot rock from the core mantle boundary is less dense than overlying mantle and slowly rises, forming plume conduits that can reach the surface as hotspots. The D layer is also where subducted slabs accumulate, potentially influencing core heat flow and magnetic field generation. Iron is important in the lower mantle. Ferropericlase contains significant iron, and iron's behavior changes with depth. At pressures above about 500,000 atmospheres, reached around 1,000 miles depth, iron in ferropericlase undergoes a spin transition, changing its electronic configuration. This affects the mineral's density and how it conducts heat, influencing mantle dynamics. Recent studies suggest post-perovskite, another high-pressure mineral, might exist in the lowermost mantle. At the extreme pressures of D, bridgmanite might transform into post-perovskite, which has even denser packing. Evidence for this comes from seismic discontinuities in D that match predicted depths for the bridgmanite to post-perovskite transition. If confirmed, this would be another phase transition, adding complexity to the lowermost mantle. The lower mantle is a vast, slow-moving region where rock circulates over hundreds of millions of years, transferring heat from Earth's core to the upper mantle and surface. It's chemically simpler than the crust, but dynamically complex, with slabs sinking, plumes rising, and large-scale structures influencing the entire system. At 1,800 miles depth, we reach the core mantle boundary, the most dramatic transition in Earth's interior. Above is solid rock, however hot and dense. Below is liquid iron, marking the outer core. The contrast is sharp. Rock gives way to metal, solid to liquid, slow convection to rapid flow. Temperature jumps from perhaps 3,500 degrees Celsius in the lowermost mantle to 4,500 degrees Celsius at the top of the outer core. This boundary is critical for Earth's dynamics. The core's heat drives mantle convection. The mantle's structure influences core flow and magnetic field generation. Interaction between core and mantle may cause variations in Earth's rotation and magnetic field. The core-mantle boundary is where Earth's rocky exterior meets its metallic heart. We've descended 1,800 miles through rock that gets progressively hotter, denser, and more alien. But we're only halfway to Earth's center. The core iron instead of rock awaits below, with even more extreme conditions. It's time to leave the realm of rock and enter the realm of metal. At the core mantle boundary, everything changes. Above is solid rock, below is liquid iron. Above, seismic shear waves propagate. Below, liquids don't support shear. This distinction, discovered in 1906 by Richard Oldham, revealed the outer core's existence and liquid state. The outer core extends from 1,800 miles to 3,200 miles depth, a layer 1,400 miles thick, larger than the Moon. It's composed primarily of iron, with about 5 to 10% lighter elements: sulfur, oxygen, silicon, carbon, hydrogen, whose exact identities and proportions are still debated. These light elements are crucial. Pure iron at core pressures would be denser than seismic observations indicate. Adding lighter elements reduces density to match observations. The outer core is entirely liquid. Temperature ranges from about 4,500 degrees Celsius at the top to 6,000 degrees Celsius at the bottom. Pressure ranges from 1.3 million atmospheres at the top to 3.3 million atmospheres at the inner core boundary. At these pressures, the iron melting point is around 5,000 to 6,000 degrees Celsius, and the outer core's temperature slightly exceeds this, keeping it molten. Liquid iron in the outer core flows vigorously. Convection currents driven by cooling from above and heat from below circulate the liquid metal at speeds of perhaps 0.1 to 0.5 millimeters per second, slow by everyday standards but fast compared to mantle convection. These currents are complex, with turbulent eddies, upwellings, and downwellings creating a roiling mass of molten metal. This motion generates Earth's magnetic field through the geodynamo process. Moving electrically conductive fluid, liquid iron, in the presence of a magnetic field generates electric currents, which in turn produce magnetic fields. If conditions are right, these generated fields can reinforce the original field, creating a self-sustaining dynamo. Earth's outer core provides ideal conditions: large volume of liquid metal, rapid convection, and rotation from Earth's spin. The geodynamo has operated for at least 3.5 billion years, based on magnetized rocks that old. The magnetic field it produces extends far into space, creating the magnetosphere that shields Earth from solar wind and cosmic radiation. Without this field, solar wind would strip away the atmosphere over millions of years, as happened on Mars when its magnetic field failed. Earth's magnetic field is complex. It's approximately dipolar, like a bar magnet with north and south poles, but with significant deviations. The magnetic North Pole doesn't align with the rotation axis and wanders slowly, currently moving from northern Canada towards Siberia at about 30 miles per year. The field's strength varies across Earth's surface, and it's weakening overall about 5% per century over the past 150 years. The field occasionally reverses, with magnetic north and south poles swapping. Paleomagnetic studies of ancient rocks show this has happened hundreds of times over Earth's history, at irregular intervals averaging a few 100,000 years. The last reversal was 780,000 years ago. During reversals, which take a few thousand years to complete, the field weakens and becomes complex, with multiple poles. Life survives these reversals. They occur too frequently in the geological record for them to cause mass extinctions, though increased radiation exposure during weak field periods might have biological effects. What drives outer core convection? Primarily, it's cooling. The core is slowly losing heat to the mantle. As the outer core cools, iron crystallizes onto the inner core, releasing latent heat and light elements, which don't fit well into the solid inner core's crystal structure. The released light elements are buoyant and rise through the outer core, driving compositional convection alongside thermal convection. This process is crucial for the geodynamo. Pure thermal convection might not suffice to maintain the magnetic field, but compositional convection from inner core growth provides additional energy. As long as the core continues cooling and the inner core continues growing, the geodynamo should keep running. The outer core rotates slightly faster than the mantle, a phenomenon called superrotation. Studies of seismic waves passing through the inner core suggest the inner core rotates faster than the mantle by about 0.3 to 0.5 degrees per year. The outer core's rotation is harder to measure directly, but theoretical models suggest it also superrotates, though by a smaller amount. This differential rotation between core, mantle, and crust affects Earth's rotation rate and day length over decades to centuries. Seismic studies reveal structure in the outer core. While it's liquid and thus lacks the rigid structure of the mantle, seismic waves show velocity variations that indicate temperature or compositional variations. Some regions transmit waves slightly faster or slower, suggesting lateral variations in the outer core's properties. The outermost outer core, just below the core mantle boundary, may have a distinct layer with different properties. This layer, if it exists, might result from reactions between iron and mantle rock, chemical stratification, or thermal effects. Evidence is debated, but some seismic studies suggest complexities at the top of the outer core. At the bottom of the outer core, near the inner core boundary, conditions become more extreme. Temperature approaches 6,000 degrees Celsius, roughly the temperature of the Sun's surface. Pressure exceeds 3 million atmospheres. Iron at these conditions behaves in ways difficult to study experimentally. Labs can briefly achieve such pressures using diamond anvil cells or shock compression, but sustaining them long enough for detailed study is challenging. Iron's properties at core conditions affect the geodynamo. Its electrical conductivity, thermal conductivity, viscosity, and how it mixes with lighter elements all influence core flow and magnetic field generation. Advances in high-pressure experiments and computational modeling are gradually improving our understanding, but uncertainties remain. One mystery is the exact light element composition. Seismic observations indicate the outer core's density is about 5 to 10% less than pure iron at those pressures. Likely candidates for the light elements include sulfur, oxygen, silicon, carbon, and hydrogen. Each has different effects on iron's properties, so identifying which are present and in what amounts is important for understanding core dynamics. Sulfur is a strong candidate. Iron-sulfur alloys melt at lower temperatures than pure iron, and sulfur is cosmically abundant. Oxygen and silicon are also plausible, coming from reactions with mantle silicates during Earth's formation. Carbon and hydrogen are possibilities, though less certain. The true composition might be a mixture of several elements. The outer core's convection patterns are three-dimensional and time-dependent. Numerical simulations of the geodynamo show complex flow structures. Columnar vortices aligned with Earth's rotation axis, sheets of rising and sinking fluid, and time-varying patterns that cause magnetic field changes. These simulations match many observed features of Earth's magnetic field, including its strength, structure, and secular variation, slow changes over decades to centuries. Geomagnetic jerks, sudden changes in the rate of magnetic field change, might result from rapid flow changes in the outer core. Satellite missions like Swarm, launched by ESA, measure Earth's magnetic field precisely, tracking these changes and providing data to constrain core flow models. The outer core is a dynamic, turbulent layer where liquid iron flows rapidly, by geological standards, generating the magnetic field that makes Earth habitable. It's a layer we can never directly sample. No material can withstand the pressure and temperature, but we can infer its properties from seismology, magnetic field observations, and theoretical modeling. At 3,200 miles depth, we reach the inner core boundary, the transition from liquid to solid iron. Here, pressure is so high that despite temperatures around 6,000 degrees Celsius, iron solidifies into a crystalline structure. We're entering the final layer of our journey, the inner core. The inner core is Earth's center, a solid sphere of iron about 760 miles in radius, roughly the size of the Moon. It's the hottest, densest part of the planet, yet also in some ways the simplest, a solid ball of iron crystals suspended in the liquid outer core, isolated from the rest of Earth by 3,200 miles of molten metal and rock. The inner core's existence was discovered in 1936 by Danish seismologist Inge Lehmann, who noticed that seismic waves from earthquakes sometimes arrived at unexpected times and places. She deduced that some waves were passing through the core's center and being refracted by a solid inner core, while others were reflected or refracted differently by the liquid outer core. Her discovery revealed the core's two-part structure. The inner core is solid despite temperatures around 6,000 degrees Celsius because of immense pressure over 3.3 million atmospheres at its outer edge, increasing to about 3.6 million atmospheres at Earth's center. At these pressures, iron's melting point exceeds 6,000 degrees Celsius, so iron solidifies even at such extreme temperatures. This is counterintuitive. At the surface, iron melts at about 1,540 degrees Celsius. But pressure raises melting points, and core pressures are so high that iron remains solid despite being as hot as the sun's surface. The inner core is primarily iron, probably with about 5% nickel and traces of lighter elements. It crystallizes in a hexagonal, close-packed structure at inner core pressures, though some studies suggest other structures might be stable. The exact crystal structure matters for understanding seismic observations, since seismic wave speeds depend on crystal orientation. One of the inner core's most intriguing features is seismic anisotropy. Seismic waves travel faster in some directions than others. Specifically, waves traveling parallel to Earth's rotation axis, pole to pole, move about 3% faster than waves traveling in the equatorial plane. This suggests the inner core's crystals are aligned with their fast axes oriented roughly north-south. Why would crystals align this way? Likely explanations involve the inner core's growth and the forces acting on it. As the inner core grows by freezing iron from the outer core, Crystals might align with flow patterns in the liquid outer core or with magnetic field lines. Alternatively, slow convection in the inner core. Despite being solid, it can flow extremely slowly over millions of years, might align crystals. The exact mechanism is still debated. The inner core's anisotropy isn't uniform. The Western Hemisphere beneath the Americas and the Atlantic shows different anisotropy than the Eastern Hemisphere beneath Asia and the Pacific. This hemispherical dichotomy suggests asymmetric growth or structure in the inner core. Perhaps the inner core is freezing faster on one side than the other, or maybe it's slowly convecting in a pattern that creates east-west differences. Some studies suggest the inner core has layers. Seismic data hint at an innermost inner core, a central region about 300 miles in radius, where anisotropy is even stronger and oriented differently. If real, this innermost core might represent a change in crystal structure or a distinct growth phase in Earth's history. The evidence is tentative, based on rare seismic waves that pass through the core's center, but it's intriguing. The inner core is growing. As Earth slowly cools, the core cools too, and iron freezes onto the inner core's surface. The growth rate is about 1 millimeter per year slow, but over millions of years it adds up. About 1 billion years ago, the inner core might have been significantly smaller, perhaps half its current radius. Before that, the inner core might not have existed at all. The entire core was liquid. Inner core growth affects the geodynamo. When iron crystallizes onto the inner core, light elements sulfur, oxygen, silicon, etc. are excluded. They don't fit into the solid iron's crystal structure. These light elements are released into the outer core, where they're buoyant and drive compositional convection. This convection, combined with thermal convection, powers the geodynamo. Without inner core growth, the geodynamo might weaken or fail. The inner core's temperature is difficult to measure directly, but estimates range from about 5,400 degrees Celsius to 6,000 degrees Celsius. The uncertainty arises from uncertainty in iron's melting point at core pressures. Experimental measurements at such extreme conditions are challenging. Recent diamond anvil cell experiments and theoretical calculations are converging on values around 6,000 degrees Celsius, similar to the Sun's surface temperature. Despite being solid, the inner core isn't static. It can deform slowly over geological time, a process called solid-state creep. Stress from the outer core's convection, from Earth's rotation, or from tidal forces can cause the inner core to slowly flow. This flow is extremely slow, much slower than mantle convection, but over millions of years it can rotate the inner core or rearrange its crystals. Evidence suggests the inner core rotates faster than the mantle's superrotation mentioned earlier. By analyzing seismic waves over decades, scientists have detected changes in travel times that suggest the inner core is rotating about 0.3 to 0.5 degrees per year faster than the mantle. Over a century, the inner core rotates about 1 full degree more than Earth's surface. This differential rotation might result from magnetic coupling with the outer core's flow. Some studies question superrotation, suggesting instead that the inner core oscillates or has more complex motion. The debate continues, with different data sets and analysis methods giving different results. Resolving this requires long-term monitoring of seismic waves passing through the inner core, a challenging task given that suitable earthquakes and receiver locations are rare. The inner core's composition affects its properties. Pure iron at core conditions would be denser than seismic observations suggest, indicating light elements are present. But the inner core has fewer light elements than the outer core. They're preferentially excluded during freezing, so the inner core is denser. The exact composition determines crystal structure, seismic velocities, electrical conductivity, and how the inner core responds to stress. Could the inner core have differentiation, a distinct core within the core? Some theoretical models suggest that at the extreme pressures of Earth's center, iron might separate into different phases, or that extremely heavy elements like uranium or platinum might sink to the very center. Direct evidence is lacking, but it's an intriguing possibility. The inner core is the endpoint of our journey Earth's center, about 3,960 miles below the surface where we started. Here, pressure exceeds 3.6 million atmospheres, 360 gigapascals. Temperature is around 6,000 degrees Celsius. Density is about 13 grams per cubic centimeter, 13 times denser than water. Conditions are so extreme that matter behaves in ways difficult to comprehend, studied only through indirect seismic observations and high-pressure experiments. Standing, if one could, at Earth's center, you'd experience zero net gravity. The mass of Earth surrounds you equally in all directions, with gravitational pulls cancelling out. You'd be weightless, floating at the center of a 13,000-kilometer diameter sphere of rock and metal, compressed by its own gravity to immense pressures and temperatures. It's perhaps the most alien environment in the solar system, more extreme than the surface of Venus, the depths of Jupiter, or the vacuum of space. Yet this tiny, hidden sphere, less than 1% of Earth's volume, plays a crucial role. Its growth drives the geodynamo. Its presence affects Earth's rotation. Its formation, billions of years ago, marked a major transition in Earth's evolution. The inner core is Earth's heart, hidden but vital. We've descended from surface to center, layer by layer. Now let's step back and consider the processes and forces that make Earth's interior so dynamic. Heat flow, pressure, and the motion of materials over geological time. Heat is fundamental. Earth's interior is hot. Temperatures range from hundreds of degrees near the surface to 6,000 degrees Celsius at the core. This heat comes from two sources: primordial heat left over from Earth's formation, and radiogenic heat from radioactive decay. When Earth formed 4.5 billion years ago, collisions of planetesimals released enormous energy, heating the planet. Differentiation ions sinking to form the core released gravitational potential energy that further heated Earth. The young Earth was probably partly or entirely molten. Over 4.5 billion years, Earth has cooled, but slowly the planet is large, and rock conducts heat poorly. Radioactive decay of uranium-238, uranium-235, thorium-232, and potassium-40 inches, the crust and mantle produces heat continuously. These isotopes decay over billions of years, releasing energy, About half of Earth's current heat flow comes from radioactive decay. The other half is primordial heat slowly escaping. Heat flows from Earth's interior to the surface at an average rate of about 47 terawatts, equivalent to about 10,000 large power plants. This heat flow is tiny compared to the energy Earth receives from the Sun, about 174,000 terawatts. But over geological time it drives plate tectonics, mantle convection, and volcanism. Heat escapes through several mechanisms. Conduction heat flowing through solid material occurs in the lithosphere. Convection material circulating, carrying heat with it, occurs in the mantle and outer core. Radiation plays a minor role. Near the surface, water circulating through hot rock, hydrothermal systems, transfers significant heat. Mid-ocean ridges are major heat loss sites. Here, hot mantle rises, partially melts, and erupts as basalt, creating new oceanic crust. Heat flows through the newly formed crust at rates 5 to 10 times higher than the global average. As the crust moves away from the ridge and ages, it cools and heat flow decreases. Old oceanic crust has low heat flow, similar to continents. Hotspots also transfer heat, though less efficiently than ridges. Mantle plumes bring hot rock from deep in the mantle to the surface, resulting in volcanism. Hawaii, Iceland, Yellowstone, all are surface expressions of mantle plumes transferring heat from depth. Pressure increases with depth as the weight of overlying rock compresses material below. Pressure is a scalar, it acts equally in all directions. At modest depths, pressure follows a simple relationship. It increases by about 0.3 atmospheres per meter of depth, assuming rock density of 3 grams per cubic centimeter. But at great depths, material becomes so compressed that density increases with depth, causing pressure to increase faster than linearly. At the core mantle boundary, pressure is about 1.3 million atmospheres. At Earth's center, it's about 3.6 million atmospheres, roughly 360 gigapascals. High pressure changes material properties. It increases density, raises melting points, alters crystal structures, affects electrical and thermal conductivity, and changes how materials deform. Minerals stable at the surface become unstable at depth, transforming into denser forms. These phase transitions occur at specific depths, creating seismic discontinuities. The balance between temperature and pressure determines whether material is solid, liquid, or partially molten. The mantle is solid despite high temperatures because pressure raises melting points. The outer core is liquid despite even higher pressure because temperature is high enough to exceed the melting point. The inner core is solid again because pressure is so immense that the melting point exceeds even core temperatures. Material in Earth's interior moves, driven by buoyancy forces from temperature and composition differences. Warm material is less dense and rises. Cool material is denser and sinks. This convection occurs in the mantle and outer core, albeit at vastly different rates. Mantle convection is slow rock rises or sinks at a few centimeters per year. Over millions of years, this motion drives plate tectonics. Oceanic plates spread apart at ridges where hot mantle rises and partially melts. Plates converge at subduction zones where cold oceanic lithosphere sinks back into the mantle. Continents, being less dense, don't subduct. Instead, they collide, forming mountains. The Wilson cycle describes how continents drift, collide, and split over hundreds of millions of years. Supercontinents like Pangaea form when continents collide, then break apart as new ocean basins open. This cycle has repeated several times in Earth's history. Currently, the Atlantic is widening. North America and Europe are drifting apart at about 2 to 3 centimeters per year, while the Pacific is shrinking as subduction consumes oceanic crust faster than spreading creates it. Mantle convection is three-dimensional and time-varying. Convection cells don't have simple up and down flow, but are chaotic and turbulent. Computer simulations show complex patterns, plumes, slabs, large-scale circulation, and small-scale turbulence. The mantle isn't a simple convection cell, but a complex dynamic system. Outer core convection is faster liquid ion flows at millimeters per second. This rapid, by geological standards, convection is turbulent and three-dimensional, generating Earth's magnetic field through the geodynamo. The flow patterns are complex, with columnar vortices, rising plumes, sinking downwellings, and time-varying structures. Coupling between mantle and core affects both. The core's magnetic field exerts torque on the electrically conductive lower mantle, potentially influencing mantle flow. Conversely, mantle convection patterns might influence core flow by affecting heat transfer across the core mantle boundary. These interactions are subtle, but might cause long-term variations in Earth's rotation rate and magnetic field. Earth's rotation affects convection. The Coriolis effect causes moving material to curve rather than moving in straight lines. In the mantle, Coriolis effects are weak because flow is so slow, but they might influence large-scale circulation. In the outer core, Coriolis effects are strong, organizing convection into columnar structures aligned with Earth's rotation axis. These columns are key to geodynamo action. Tidal forces from the moon and sun deform Earth slightly, causing rock and iron to flex. This tidal dissipation converts orbital energy into heat, a tiny contribution to Earth's heat budget, but measurable. Over billions of years, tidal dissipation has slowed Earth's rotation. Days were shorter in the past and pushed the moon farther away. It recedes about 3.8 centimeters per year. Plate tectonics is unique to Earth among the solar system's rocky planets. Venus, Mars, Mercury, and the Moon all lack plate tectonics. Why Earth has it is debated. Likely factors include Earth's size, large enough to stay hot, water which weakens rocks and aids subduction, and perhaps specific initial conditions. Plate tectonics recycles crust, regulates climate by controlling CO2 levels, and creates diverse environments. It may be essential for complex life. Earth's interior is a heat engine, with heat flowing from the hot core to the cool surface. This flow drives convection, which drives plate tectonics, which shapes the surface. Volcanoes, earthquakes, mountains, ocean basins All are surface expressions of Earth's internal heat engine at work. How do we know what's inside Earth? We can't see it, can't drill to it, can't sample most of it. Yet we've mapped Earth's interior in remarkable detail. This knowledge comes from multiple sources: seismology, experiments, theory, and rare samples. Seismology is the primary tool. Earthquakes generate waves that propagate through Earth. By detecting these waves at seismometers worldwide, we can infer the structure they've passed through, much like a medical CT scan uses X-rays to image the body's interior. There are several types of seismic waves. P waves, primary waves, are compressional like sound waves. They compress and expand material as they propagate. P waves can travel through solids and liquids. S waves, secondary waves, are shear waves. They oscillate perpendicular to their direction of travel. S waves can only propagate through solids. Liquids don't support shear. When an earthquake occurs, P waves and S waves radiate outward. P waves travel faster and arrive first at seismometers. S waves arrive later. By measuring arrival times and amplitudes, seismologists determine the waves' paths and the properties of material they traversed. Some waves travel directly through Earth's interior. These are body waves. Others travel along the surface waves, which are slower but often larger in amplitude. Surface waves are useful for studying the crust and uppermost mantle. Body waves probe deeper. Seismic waves refract and reflect at boundaries where properties change. The core mantle boundary reflects and refracts waves strongly because of the large velocity contrast between rock and liquid iron. The inner core boundary also creates reflections and refractions. By analyzing these, we map Earth's layers. Seismic tomography extends this to 3D imaging. By analyzing thousands of earthquakes recorded at hundreds of seismometers, scientists create 3D maps of seismic velocity variations throughout the mantle. Fast regions correspond to cold, dense rock, subducted slabs. Slow regions correspond to hot, buoyant rock, plumes. This reveals mantle convection patterns in stunning detail. Seismology discovered Earth's layers. The Moho was found in 1909. The core mantle boundary was identified by 1914. The liquid outer core was established by 1926. The solid inner core was discovered in 1936. Each discovery came from careful analysis of seismic wave behavior. But seismology has limitations. It provides indirect information, wave speeds, not composition. Interpreting seismic data requires knowing how waves travel through different materials at high pressure and temperature. This is where experiments and theory come in. High-pressure experiments recreate core and mantle conditions in the lab. Diamond anvil cells squeeze samples between gem-quality diamonds, reaching pressures exceeding core pressures, though only in tiny volumes. Heating the sample with lasers allows simultaneous high pressure and temperature. Scientists measure properties like density, crystal structure, and wave speeds under these conditions. Shock compression uses high-velocity impacts to momentarily achieve extreme pressures and temperatures. By analyzing how shock waves propagate through samples, scientists infer properties at core conditions. These experiments are challenging conditions, last microseconds, Measurements must be extremely fast, and samples are often destroyed. Results from experiments are combined with theoretical calculations. Quantum mechanics and computational modeling predict material properties at extreme conditions, complementing experiments. Over decades, this combined approach has refined our understanding of iron's behavior at core conditions, mantle mineral properties, and how materials respond to pressure and temperature. Rare samples provide direct evidence. Meteorites, particularly iron meteorites, are samples of differentiated asteroids' cores, iron-nickel alloys similar to Earth's core. They provide clues about core composition and cooling rates. Xenoliths, fragments of mantle brought to the surface by volcanic eruptions, provide actual mantle samples. Kimberlite pipes bring xenoliths from depths of 90 to 120 miles, including diamonds and their inclusions. Ophiolites, sections of oceanic crust and upper mantle thrust onto continents by tectonic forces, expose mantle rock at the surface. These samples are invaluable, but biased. We only get material from specific depths and conditions where it can reach the surface. The lower mantle, outer core, and inner core remain inaccessible except through indirect methods. Gravity measurements help constrain Earth's mass distribution. Earth's overall density is about 5.5 grams per cubic centimeter, much denser than surface rocks, 2.7 to 3 grams per cubic centimeter, indicating a dense iron core. By measuring tiny variations in Earth's gravity field using satellites like GRACE, scientists map density variations in the crust and mantle. Earth's moment of inertia, how mass is distributed relative to the rotation axis, also constrains interior structure. A planet with mass concentrated in a core has a smaller moment of inertia than one with uniform density. Earth's measured moment of inertia confirms mass is concentrated in the core. Magnetic field observations constrain core properties. The geodynamo depends on outer core flow, which depends on core composition, temperature, and viscosity. By measuring the magnetic field's structure and time variations, secular variation, scientists infer core flow patterns and properties. Computational models synthesize all this information. Geodynamo simulations model outer core flow and magnetic field generation. Mantle convection models simulate plate tectonics and plume dynamics. These models are tested against observations, seismic structure, magnetic field, plate motions, heat flow. When models match observations, we gain confidence in our understanding. Uncertainty remains. The outer core's exact composition is debated. The inner core's structure is poorly constrained. The D layer's properties are unclear. Lower mantle dynamics are uncertain. Each new observation, a better seismic tomography model, a new experiment at higher pressure, a refined geodynamo simulation improves our understanding but also raises new questions. Studying Earth's interior is detective work. We gather clues from many sources, piece them together, test hypotheses, and gradually build a picture of the hidden world beneath our feet. It's one of science's great achievements, mapping and understanding a realm we can never directly visit. Earth's magnetic field is both familiar and mysterious. Compasses have guided travelers for centuries, relying on the field's north-south orientation. Yet the field's origin, the geodynamo deep in the outer core, was only understood in the mid-20th century, and many details remain unclear. The magnetic field resembles a bar magnet inside Earth, with field lines emerging from the southern hemisphere, looping through space and re-entering in the northern hemisphere. But Earth's interior isn't a permanent magnet. At core temperatures, iron loses permanent magnetization. Thermal energy disrupts magnetic domains. Earth's field is generated by electric currents in the liquid outer core. The geodynamo is a self-sustaining process. Moving electrically conductive fluid, liquid iron, through a magnetic field generates electric currents, which produce magnetic fields. If the geometry is right, the generated field reinforces the original field, creating a positive feedback loop. This is a dynamo converting kinetic energy of fluid motion into magnetic energy. For a dynamo to work, several conditions must be met. There must be a conducting fluid. Earth's iron outer core qualifies. The fluid must be in motion convection, driven by cooling and compositional buoyancy. The flow must be sustained. Earth's internal heat provides energy. And the geometry must support field generation. Earth's rotation organizes flow into patterns that amplify fields. The process is complex. Numerical simulations of the geodynamo solve the equations of fluid dynamics and electromagnetism in a rotating spherical shell representing the outer core. These simulations produce magnetic fields remarkably similar to Earth's, with similar strength, structure, and time variations. Success of these models confirms our basic understanding of the geodynamo. But mysteries remain. The field's detailed structure, why it has certain features and not others, isn't fully explained. The causes of geomagnetic jerks, sudden changes in secular variation, are debated. The trigger for magnetic reversals is unknown. Magnetic reversals are particularly intriguing. The field has reversed hundreds of times over Earth's history at irregular intervals. The average time between reversals is a few 100,000 years, but intervals range from tens of thousands to tens of millions of years. The most recent reversal was 780,000 years ago, longer than average, leading some to speculate another reversal might be due. During a reversal, the field weakens and becomes complex. Instead of a simple dipole, multiple poles appear, and the field's intensity drops perhaps to 10–20% of its normal value. The transition takes a few thousand years, during which the magnetic poles wander erratically. Eventually, a new dipole establishes with opposite polarity. What causes reversals? Likely, they're a natural consequence of chaotic geodynamo dynamics. Computer simulations of the geodynamo spontaneously produce reversals without requiring external triggers. The chaotic flow in the outer core occasionally enters a state where the dipole field weakens and reverses. It's somewhat random, like turbulence in a fluid. Reversals don't harm life. The paleomagnetic record shows no correlation between reversals and mass extinctions. However, during low field periods, Earth receives more cosmic radiation. The magnetosphere is weaker, allowing more high-energy particles to reach the atmosphere. This might affect cloud formation, climate, or mutation rates, but effects are likely subtle. The field isn't a perfect dipole even during stable periods. It has quadrupole and octupole components, more complex patterns involving 4 or 8 poles. The dipole dominates, but other components are significant. The non-dipole field changes faster than the dipole, with patterns drifting westward at about 0.2 degrees per year, a phenomenon called westward drift, attributed to outer core flow. The South Atlantic anomaly is a region where the field is particularly weak, about half the global average. Satellites passing through this region experience higher radiation exposure. The anomaly has existed for centuries and is slowly moving westward. Its cause is debated, possibly a region of reversed flux in the core or an artifact of the tilt between the magnetic and rotation axes. The field's strength has decreased about 10% since measurements began in the 1840s, and about 5% per century on average over the past millennium, inferred from archaeological and geological records. This decay might be part of normal variation, or it might indicate an impending reversal. Predicting reversals is difficult because the geodynamo is chaotic and we have only a few thousand years of detailed data. Ancient magnetic fields are recorded in rocks. When lava cools, iron minerals in it align with Earth's field, becoming fossilized compasses. Sedimentary rocks also record the field as magnetic particles settle and align. By studying rocks of different ages, we reconstruct ancient magnetic fields, their direction and intensity. Paleomagnetism has revealed much. It showed that continents have moved drift, changes the apparent position of magnetic poles over time. It demonstrated reversals occur frequently. It constrained the age of the geodynamo at least 3.5 billion years, possibly older. And it showed the field's intensity has varied, sometimes being stronger or weaker than today. The field extends into space, forming the magnetosphere, a region where Earth's magnetic field dominates over the solar wind, charged particles from the Sun. The magnetosphere is compressed on the Sun-facing side, about 10 Earth radii out, and stretched into a long tail on the night side, extending beyond the Moon's orbit. The magnetosphere shields Earth from solar wind. Without it, solar wind would interact directly with the atmosphere, gradually stripping it away over millions of years. Mars lost its magnetic field early in its history, and solar wind has since removed much of its atmosphere, leaving Mars cold and dry. Venus never had a strong field and also lost much of its atmosphere to space. Geomagnetic storms occur when solar activity disrupts the magnetosphere. Solar flares or coronal mass ejections send bursts of charged particles toward Earth. When they reach Earth, they compress the magnetosphere, inducing currents that heat the upper atmosphere and create auroras, the northern and southern lights. Strong storms can disrupt satellites, power grids, and communication systems. Understanding the magnetic field is important for navigation, satellite operations, and studying space weather. It's also a window into Earth's deep interior. The field's variations reflect flow patterns in the outer core, providing information about core dynamics that seismology can't access. By monitoring the field closely, using satellites like SWARM, we track core processes in near real time. The geodynamo has operated for most of Earth's history, generating a field that has protected the atmosphere and enabled life. It's powered by Earth's internal heat, sustained by convection in the liquid outer core, and organized by Earth's rotation. As long as the core continues cooling and convecting, the geodynamo should keep running, maintaining the magnetic shield that makes Earth habitable. We've completed our impossible journey from the surface down through crust, mantle, outer core, and inner core, reaching Earth's center 3,960 miles below where we started. We've traveled through rock that becomes progressively hotter, denser, and more alien with depth. We've passed from brittle crust through flowing mantle to liquid iron and finally to a solid iron sphere as hot as the sun's surface. This hidden world, though forever beyond direct human reach, is understood in remarkable detail. Seismology maps Earth's layers with precision. High-pressure experiments reveal how materials behave at core conditions. Theoretical models simulate mantle convection and the geodynamo. Together, these tools have illuminated what lies beneath our feet. Earth's interior is not static. It's a dynamic system where heat flows, materials convect, and continents drift. The mantle circulates over millions of years, driving plate tectonics that reshape Earth's surface. The outer core flows rapidly, generating the magnetic field that shields life from radiation. The inner core grows slowly, releasing energy that sustains the geodynamo. This dynamism makes Earth unique among rocky planets. Venus lacks plate tectonics, leading to a stagnant surface and runaway greenhouse. Mars cooled too quickly, its magnetic field dying and atmosphere thinning. Mercury is too small to retain internal heat. Only Earth maintains the vigorous convection that recycles crust, regulates climate, and creates diverse environments. The interior influences the surface in countless ways. Volcanic eruptions bring deep material to the surface, releasing gases that form the atmosphere and oceans. Earthquakes result from plate motions driven by mantle convection. Mountains form where continents collide, pushed together by the slow but inexorable motion of tectonic plates. The magnetic field generated in the core protects the atmosphere from solar wind. Even life depends on Earth's interior. Plate tectonics recycles carbon, regulating CO2 levels and maintaining habitable temperatures. Volcanic outgassing provided the water for oceans and the gases for the atmosphere. Geothermal energy may have supported early life. The magnetic field shields organisms from harmful radiation. Without a dynamic interior, Earth would be a cold, dead world. Our journey has revealed the planet's structure, but questions remain. What exactly is the composition of the outer core? How does the geodynamo really work in detail? Why do magnetic reversals occur when they do? How does the D layer influence mantle dynamics? Does the inner core have an innermost layer with different properties? Each advance raises new questions. The more we learn, the more we realize how much we don't know. Earth's interior is immensely complex, with processes operating over timescales from seconds, seismic waves, to billions of years, core cooling. Understanding it fully will require generations of research. Yet what we've learned is profound. We know Earth has layers: crust, mantle, outer core, inner core. We know their compositions, temperatures, pressures, and how they move. We've mapped seismic structures in 3D, revealing slabs, plumes, and convection patterns. We've simulated the geodynamo, producing magnetic fields matching observations. We've measured continental drift and traced plate motions back hundreds of millions of years. This knowledge is practical. Understanding plate tectonics helps predict earthquakes and volcanic eruptions. Mapping Earth's interior improves our ability to locate mineral deposits. Studying the magnetic field helps protect satellites and power grids from geomagnetic storms. Geothermal energy taps Earth's internal heat for power generation. But the knowledge is also profound in another way. It reveals Earth's history and future. The layered structure formed during differentiation 4.5 billion years ago. The inner core began growing perhaps 1 to 2 billion years ago. Plate tectonics has operated for at least 3 billion years, perhaps longer. The magnetic field has shielded Earth for most of its history, enabling life to evolve and thrive. Looking forward, Earth will continue cooling. The mantle will convect more slowly. The inner core will grow, perhaps eventually filling the entire core billions of years from now. Plate tectonics might slow or stop as the mantle cools and stiffens. The magnetic field could weaken if core convection slows, but these changes occur over billions of years far into the future. For now, Earth's interior remains active and vigorous. Beneath our feet, rock flows, iron convects, and the planet's internal heat engine powers the processes that make Earth dynamic and habitable. We live on the thin skin of an immense, complex, ever-changing sphere. As you drift towards sleep, imagine the Earth beneath you. Solid rock extending miles down, mantle flowing slowly, carrying continents on its surface. Liquid iron swirling in the outer core, generating the magnetic field that surrounds the planet. A solid inner core growing slowly, releasing energy that sustains Earth's activity. You're connected to all of it. The atoms in your body were forged in stars and delivered to Earth billions of years ago. The ground beneath you is part of a tectonic plate, moving slowly but inexorably. The air you breathe was exhaled by volcanoes, ultimately sourced from Earth's interior. The magnetic field sheltering you is born in the planet's core. Earth is not just a platform for life, but an active, dynamic system. Its interior processes have shaped the surface, created the atmosphere, and enabled life. Understanding Earth's hidden depths gives us perspective on our place in the cosmos. We live on a remarkable planet, large enough to stay warm, with just the right chemistry to sustain plate tectonics and a magnetic field at just the right distance from the sun to maintain liquid water. Tomorrow, the sun will rise, pulled across the sky by Earth's rotation. Beneath your feet, the mantle will continue its slow circulation. The outer core will flow, sustaining the magnetic field. The inner core will grow imperceptibly. These processes, operating over timescales from seconds to billions of years, make Earth the vibrant, living world we inhabit. Rest well, knowing that beneath the surface lies a hidden world of wonder, extreme yet orderly, alien yet essential, forever beyond reach yet intimately connected to everything we experience. The journey to Earth's center is impossible for humans, but in imagination and understanding, we've made that journey, discovering that our planet's depths are as fascinating as the cosmos beyond. Sweet dreams, fellow traveler. May your rest be as deep as Earth's mantle, as stable as its inner core, as encompassing as its magnetic field. The planet beneath you is vast and ancient, dynamic and enduring. You are part of it, connected to its deepest layers through the atoms you're made of and the processes that sustain life. Sleep well, cradled by the earth, under its protective magnetic shield, on its thin but precious surface.